see if that worked. All right, let me just go ahead and start it. All right, greetings YouTube. A beautiful mind here. So I was trying to load. I was trying to load some video responses to some calculus questions, and for whatever reason, they're not loading. So what this is going to be is an alternate attempt for me to load the questions. I'm just going to do one long live stream. It's going to take me probably an hour or whatever, and I'll just try to create some timestamps or whatever for each question. But I'm going to live stream or showcase the video responses to all 5 questions. All right. All right, greetings YouTube. Beautiful mind here. We have this question, We have this question that comes from calculus, right? It asks us to consider this function f of x equals x to the power of 4 over 5 times x minus 6 quantity squared. We're asked to find the derivative, find the values of x such that f prime of x equals 0, find the values of x such that f prime of x does not exist, and find the critical numbers. Is that critical numbers or critical values? Yeah, critical numbers of f prime of x, or of the function. All right, so with that first one, we're going to find the derivative. There's about 2 or 3 different techniques at play. It's kind of a loaded question. Let me see. So the first thing is, we have this guy times this guy, all right? So that means that we would use the product rule when we're taking the derivative. The product rule for derivative is what? The first is first times the derivative of the second plus the second times the derivative of the first. All right, okay. So let me see. Okay, I got it here. All right. So if we want to find a derivative, first times the derivative of the second plus the second times the derivative of the first. Okay. So then f prime, the first is this guy, this x to the power of 4 over 5. The derivative of the second, so first I'm just going to write it as d by dx. So this d by dx just means the derivative with respect to x of the following. All right. So d by dx of this guy. So in other words, just take the derivative. So that's the first times the derivative of the second plus the second, which is this guy, times the derivative of the first, which is going to be this guy, x to the power of 4 over 5. Okay? So that's called the product rule for find a derivative. Now we're going to go back and calculate those guys in blue. All right, so the things in black, I'm just going to bring them down for now. So then f prime x to the power of 4 over 5. So now with that first derivative in blue, this guy here, we have to apply what's called the chain rule, right? So that's the second technique. That's why I said it was loaded. So the chain rule is similar to the power rule. It's going to be like the derivative of the outside function times the derivative of the inside function. Let me say that one more time. The chain rule is going to be the derivative of the outside function times the derivative of the inside function. So like if it's, kind of, if you look at it kind of like if we just got something squared, right? If we had x squared, what's the derivative of x squared? The 2 comes down, we subtract 1 from the power, so it would just be 2x. So then this is going to be 2 times that something. Then we got to say times the derivative of the inside function, right? Okay. So here, the 2 comes down, the inside stays as is, right? And we subtract 1 from the power, so it just becomes a 1. There's an implied 1 there. And then we say times the derivative of the inside function. So the derivative here, the derivative of x is 1. The derivative of negative 6, which is a constant, is going to be 0. So then 1 plus 0 is just a 1 there. Okay. So we don't necessarily need to write that times 1, but it's times 1. All right. Okay. So that's the first times the derivative of the second. Now we need to say plus the second. Again, in black, I'm just bringing it down. The derivative of the first. So that's just the power rule. The chain rule is like an extended power rule, right? So the power rule, again, the power comes down and we subtract 1 from the power. So we're going to say times, that power comes down, which is this guy. All right, we kind of did the same thing here when we took the derivative. Then we subtract 1 from that power, so we're going to get what? X to the power of a negative 1 over 5. Okay. So now we need to kind of go back and simplify and combine like terms. Let me see. Now, both of these terms, again, terms are things that we add and subtract. Factors are things that we multiply and divide. Both of these terms, and I'm referring to like this compared to this. See how they're separated by that plus? They both have this x minus 6, at least one of them. All right. So I know we could at least factor out at least one set of x minus 6. It gets a little bit, a little bit challenging to follow. So then f prime comes down. We got this x minus 6. Now in that first term, what's left? We have that 2 times x to the power of 4 over 5, okay? And then we're going to say what? Plus, there's still an x minus 6 here. Can't get anything else. We could factor out a 2, maybe. We got this 4 over 5. And that negative exponent really means it's 1 over x. I'm going to leave it as x to the negative 1 over 5 for now. Okay. I'm trying to see if I can simplify this down at all. Okay, I think I'm just going to expand it out. Did I miss anything? That move, that move to the front, that move to the front. We got our 2 times that. Okay, I'm just going to try to simplify it down some. We got this x minus 6. Alright, I'm going to bring down this 2x to the power of 4/5. I'm going to distribute here. Let me see. Now we're going to have a plus. That's a 4 over 5. Now if we got x to the power of a negative 1 over 5 times x to the power of 1, you add the powers. So that's going to be what, 4 over 5? Okay. And then it looks like it's going to be a minus 24 over 5 x to the power of negative 1 over 5. So, it didn't really help us that much. Now, it looks like we got some terms that will combine a little bit. Can we factor out that 1/5? We might be able to. Let me keep going. All right, greetings YouTube. Beautiful Mind here. We have this question, We have this question that comes from calculus, right? It asks us to consider this function f of x equals So give me a moment. I'm gonna redo how I do this. I'm gonna move the files. If I go to iMovie, that way I don't have to mess with it. New project, just a movie, videos. It should be 1, 2, 3, 4. Shiesta. Duplicate. Where are the ones from today? 1, 2, 3, 4. Oh, these, no. Some duplicates. Okay, I think they're all doubled. Okay, I think I see it now. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. Create the movie. Let's see. Okay, 1.5 hours. Okay, I think this is proper. Come on. That was definitely the last one. Okay. Let's try this again. Here. So sorry about that. Okay, we're gonna try this one more time. Let me share my screen. Start the broadcast. Optimize the video, share the audio device. I'm gonna go ahead and mute myself and pop over to the video. All right. All right. Greetings, YouTube. Beautiful mind here. We have this question. Sorry. We have this question that comes from calculus, right? It asks us to consider this function f of x equals x to the power of 4 over 5 times x minus 6 quantity squared. We're asked to find the derivative, find the values of x such that f prime of x equals 0, find the values of x such that f prime of x does not exist, and find the critical numbers. Is that critical numbers or critical values? Yeah, critical numbers of f prime of x, or of the function. Right? So with that first one, we're going to find the derivative. There's about 2 or 3 different like techniques at play. It's kind of a loaded question. Let me see. So the first thing is, we have this guy times this guy, all right? So that means that we would use what, the product rule when we're taking the derivative? The product rule for derivative is what? The first is first times the derivative of the second plus the second times the derivative of the first. All right? Okay? So let me see. Okay, I got it here. All right? So if we want to find a derivative, first times the derivative of the second plus the second times the derivative of the first. Okay? So then f prime, the first is this guy, this x to the power of 4 over 5. The derivative of the second, so first I'm just going to write it as d by dx. So this d by dx just means the derivative with respect to x of the following. All right? So d by dx of this guy. So in other words, just take the derivative. So that's the first times the derivative of the second plus the second, which is this guy, times the derivative of the first, which is going to be this guy, x to the power of 4 over 5. Okay? So that's called the product rule for find the derivative. Now we're going to go back and calculate those guys in blue. All right, so the things in black, I'm just going to bring them down for now. So then f prime x to the power of 4 over 5. So now with that first derivative in blue, this guy here, we have to apply what's called the chain rule, right? So that's the second technique. That's why I said it was loaded. So the chain rule is similar to the power rule. It's going to be like the derivative of the outside function times the derivative of the inside function. Let me say that one more time. The chain rule is going to be the derivative of the outside function times the derivative of the inside function. So like if it's, kind of, if you look at it kind of like if we just got something squared, right? If we had x squared, what's the derivative of x squared? The 2 comes down, we subtract 1 from the power, so it would just be 2x. So then this is going to be 2 times that something. Then we got to say times the derivative of the inside function, right? Okay. So here, the 2 comes down, the inside stays as is, right? And we subtract 1 from the power, so it just becomes a 1. There's an implied 1 there. And then we say times the derivative of the inside function. So the derivative here, the derivative of x is 1. The derivative of -6, which is a constant, is going to be 0. So then 1 plus 0 is just a 1 there. Okay. So we don't necessarily need to write that times 1, but it's times 1. All right. Okay. So that's the first times the derivative of the second. Now we need to say plus the second. Again, in black, I'm just bringing it down. The derivative of the first. So that's just the power rule. The chain rule is like an extended power rule, right? So the power rule, again, the power comes down and we subtract 1 from the power. So we're going to say times, that power comes down, which is this guy. All right, we kind of did the same thing here when we took the derivative. Then we subtract 1 from that power, so we're going to get what? X to the power of a -1 over 5. Okay. So now we need to kind of go back and simplify and combine like terms. Let me see. Now, both of these terms, again, terms are things that we add and subtract. Factors are things that we multiply and divide. Both of these terms, and I'm referring to like this compared to this. See how they're separated by that plus? They both have this x minus 6, at least one of them. Alright. So I know we could at least factor out at least one set of x minus 6. It gets a little bit, a little bit challenging to follow. So then f prime comes down. We got this x minus 6. Now in that first term, what's left? We have that 2 times x to the power of 4 over 5, okay? And then we're going to say what? Plus, there's still an x minus 6 here. Can't get anything else. We could factor out a 2, maybe. We got this 4 over 5. And that negative exponent really means it's 1 over x. I'm going to leave it as x to the negative 1 over 5 for now. Okay. I'm trying to see if I can simplify this down at all. Okay, I think I'm just going to expand it out. Did I miss anything? That move, that move to the front, that move to the front. We got our 2 times that. Okay, I'm just going to try to simplify it down some. We got this x minus 6. Alright, I'm going to bring down this 2x to the power of 4/5. I'm going to distribute here. Let me see. Now we're going to have a plus. That's a 4/5. Now if we got x to the power of a negative 1/5 times x to the power of 1, you add the powers. So that's going to be what, a 4/5? Okay. And then it looks like it's going to be a minus 24/5 x to the power of negative 1/5. So, you know, it didn't really help us that much. Now, it looks like we got some terms that will combine a little bit. Can we factor out that 1/5? We might be able to. Let me keep going. Now, we probably could have stopped a line or two above. Sometimes they don't require that you simplify it. I'm just trying to simplify it. Let me see. 4/5, 2/1, 5 times 2 is 10, so that's a 14/5. It's 24/5 x to the negative 1/5. Okay. This is kind of a weird answer, but this might be what it is. So this is as far as I was able to take it. So I'll just highlight this. As far as the derivative. Okay, I know we had more. Let's see. We paste. So we found the derivative. And hopefully I didn't make any mistakes, because, you know, sometimes I do make mistakes. I mean, part of it is like being able to realize when you do make a mistake and then go back and try to correct the error. Let me see. Now I could probably run this through some software to just confirm, but those numbers look so weird. But let's just kind of go with it for now. Next we want to find the values of x such that f prime is 0. So we want to set this result equal to 0 and solve. So it looks like when x is 0, nope. I was going to say when x is 0, but this x is in the denominator. So then, you know, we can't divide by 0. Again, a negative power means it's in a denominator. And if x was 0, then it would spit out an error. So because it is negative power, x equal to 0 can't be one of our results. Let me see from here. So from the first one, if we set this first factor equal to 0, then we get x equals 6. We need to set this guy to 0 and solve and see what do we get. So let me. So if we have f prime of x, we got this x minus 6, 14/5 x to the power of 4/5 minus 24/5 x to the power of negative 1/5. Okay. So if we want to find the values of x that make this 0, so we're going to set this equal to 0 and solve. All right. So then what we're using here is called a zero factor property. When two or more things multiply to give us 0, we set each factor to 0 and then solve, right? So the first one, we got this x minus, we got this x, I don't know why it's doing that. Let's see if I can fix it. Okay, let's try this now. So the first factor, there it is, x minus 6, we're going to set that equal to 0. And if we add 6 to both sides, then we get x equals 6. So that's one of our zeros. Now this other one, I'm sure there's more simplification we can do, but you know, my brain is acting weird today. So we got this 14 over 5 x to the 4 over 5 minus 24 over 5 x to the negative 1 over 5. We want to set this equal to 0 and solve. Let's see. Okay. Okay, so I'm going to rewrite this. This is what, 14 over 5 x to the 4 over 5. This is 24 over 5. That negative exponent, I'm going to rewrite it as 1 over x to the 1 over 5 equal to 0, right? So then what we can do here is multiply both sides by the LCD of our denominators, least common denominator or least common multiple. Okay. So like if we multiply both sides by what? 5x to the power of 1 over 5. So we're going to multiply all terms by 5x to the power of 1 over 5, right? So 5x to the power of 1 over 5 times that guy. This guy over here as well. And this guy over here, we're doing the same thing. And so like this is a way to clear out fractions, right? So let me see. These 5s are going to cancel each other. Now we got an x to the 1 over 5 times x to the 4 over 5. We add those powers, that looks like that just becomes what? X, right? So that first one becomes 14x. The second one, if we're multiplying by that, this cancels that, this cancels that. Looks like it's a minus 24 equals 0. Okay, well, add 24 and divide. X equals 12 over 7. Okay. So we can at least check if that actually gives us our 0. Let me see if I can pull this up. So then, like here. Okay, let's close these tabs. It's gonna be this one. Like it's still there. Reload and refresh. Okay. Okay. So what I'm gonna do to check this, all right, instead of putting, in case my derivative is wrong, what I'm going to do is work with the original. And matter of fact, let me back up just a little bit to make sure I copied it properly. Yeah, it looks right. X to the power of 4 over 5, x minus 6 squared. Okay. Okay. So let me see, I'm going to go to my y equals. I got my x to the power of 4 over 5 times, open parentheses, x minus 6, close parentheses, squared. Okay, so that's the original. Okay, so now I want to check. Now, what we're saying is that if we plug 6 into the derivative, it should output 0, right? So let's see, I think if I go to, is it list? Let's go math over here. Derivative, right? I gotta remember the syntax for this. We want to take the derivative of that function we typed in with respect to x when x is what, 6? We should get 0. I mean, that's essentially 0, but that's not exactly 0. But because it's such a small number, right? It's 5.5906 times 10 to the power of negative 7. So there are 6 zeros in front of that 5, which means that's essentially 0. Um, okay, let's try this other number. If we get another small number like that, then that's a decent omen. So when x is what? We got 12 over 7. Let's see if that works when x is 12 over 7. We should get another really small number. And it is. It has, what, 5 zeros in front of it? Okay. That's about the best we can do there. At least I can think in this moment to do. Let me see something, because I think we had at least one result. Mm-hmm. Okay. Okay, let's keep going. So, yeah, I don't know. I mean, I'm a little nervous because it's like I'm not checking it all the way, so it could be wrong. So that's where my hesitation is coming, and I'm trying to think of like if I had my 89, like a T89, I think that one is a lot more powerful. Uh, Probably GeoGebra or Desmos might be able to do this as well. I'll try that a little bit later. Find the value of x such that the derivative does not exist. So those would be values of x. Well, okay, yeah, it does not exist. What when x is 0, right? Because of remember this guy here, we had the negative exponent, so that's in the denominator. So then when x is 0, right? I think you got that one right, and that comes from here. Because that's the only time it's not going to exist is in this case because you're dealing with a fraction, right? We can't divide by 0, so that's why that one was 0. So then we write something like f prime does not exist when x equals 0, right? Main ones, this isn't like 100% of the time, but like when you're trying to like figure out does not exist, things to be on the lookout for: fractions, because we can't divide by 0, or whenever we're taking an even root, like a square root or fourth root or something like that, we can't take the square root of negative numbers. So I don't think we had an even root here because those denominators and those powers are all odd, but we did have a fraction. We can't divide by 0, so that's why that one would be when x is 0. I'll highlight it here. Okay. So then the critical numbers of the derivative, those are going to be those values of x that make the derivative either 0 or undefined. So it looks like, I still feel like I'm missing something. But we got those two values of x, the 6 and the 12 over 17. And then 0, those would be our critical numbers that we would test. We would pass through our first derivative test, like when we start graphing and things of that nature. These are our critical values. So then the critical, provided these numbers are correct, critical values are going to be x equals 6, 12, 12 over 7, or and 0. Okay. Okay, I think those were all the parts. All right, so okay. So like we use we use this in like the critical values a lot of times in like graphing, right? When we're graphing curves in calculus, this kind of information will come out in the first derivative test. And so with the first derivative test, what we're trying to find, what it's going to show us in the original graph is like either the peak of a mountain or the bottom of a valley. And these are going to occur at the critical values, right? So that's where the derivative is either 0 or undefined. So if we were to look at the original and look when x is either 6, 12 over 7, or 0, at if there are any like peaks or valleys, they would occur at these x values, right? So that's one way we can kind of verify what we're doing. So I think we already have the original in there. Let me see something. So I want to calculate the value. For instance, when x is 6, what's the corresponding y? It was 0. When x is 12 over 7, corresponding y was like 28. And when x is 0, it's 0. Okay. So then my window, the y value, we need to go up to like 35 or 40. And maybe go in steps of 5. And so again, when x is either 6, the 12 over 7, or 0, we should see either the peak of a mountain or the bottom of a valley at those points. X is 0. Looks like all three of them occurred, right? So when x is 0, you can see it. Let me see. Calculate. So for instance, when x is 0, you see it on the y-axis there. Calculate value. Okay, it might. Okay, so it might actually go down to the origin, right? As I think we did get that. So it might behave a little different, weird, because of like the exponent or whatever. But there still is the bottom of a valley, right? And then let's look at when x 12 over 7. Let's look at when x is 12 over 7. So that should be the peak of the mountain. See it there? And then when x is 6, it should be the bottom of the valley. So that's one way that we can, like, you know, we have this graphical representation. I can plot those points if you wanted, but we have a graphical representation to confirm that these critical values indeed identify, you know, the extrema of the function, right? The extrema are the maximum and the minimum, local max and the local min of the function. Okay, so we can be more confident in these results. Okay, all right. So with that, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Take care. Peace. All right, greetings YouTube, beautiful mind here. So we have this question that comes from calculus. Let's see, it says, consider this function on the closed interval from -1 to 6. We're asked to find the derivative, find the critical numbers, and find the absolute max and min. Let's see, so the derivative here doesn't look too terribly bad. Sorry, come on. There we go. Copy. All right. So for the derivative, right? Let's start here. So again, we have f of t equals t minus the cube root of t on the closed interval from -1 to 6. Okay, that's fine. Let's see. So you can kind of just do this part by part. If we focus on this guy by itself, the derivative of t is just going to be what, 1, right? The power comes down, and we subtract 1 from the power. So it's going to be 1 times t to the power of 0. T to the power of 0 is a 1, so then 1 times 1 is 1, okay? So for that first part, f prime of t, that's going to be a 1. Then we're going to say minus. Now, we got what? The cube root of t, that's the same as what? T to the power of a third. So I'll write that here. This is the same as t to the power of a third. Okay. So then when we go to take the derivative, the power comes down in front and we subtract 1 from the power. So then now it's going to become 1/3 times t to the power of a negative 2/3. Okay. So that's going to be the derivative of the original. Okay. So then next we're asked, let me go ahead and mark this. So then next we're asked to find the critical numbers. So the critical numbers are going to be those values of t that either make the derivative either 0 or undefined. So first let's go ahead and set the derivative equal to 0 and solve. So then we have this 1 minus 1/3 t to the negative 2/3. We're going to set it equal to 0. So we can add that term to both sides. We're going to have, I'm going to kind of flip it around. We got this 1/3 t to the negative 2/3 equal to 1. So what I did, I added this guy to both sides. I had 1 equals this guy, and then I just reversed the order. Instead of 1 equals this guy, I did this guy equals 1. Okay. If we want to solve, I'm going to go ahead and multiply both sides by 3. And I'm going to rewrite this guy. So this is really 1 over t to the 2/3 equals 3. So then when we have a fraction equal to another fraction, we can cross multiply. Okay, so then we're going to get 3 times t to the 2/3 equals what, 1? So essentially I said like this is over 1. I said this times that and that times that, and that's how I got this result. It's a little bit back and forth, I know, but we're almost there. Let's see. T to the power of 2/3 equals 1/3. Let me see. Okay. So to the inverse of that power, if we have t to the power of 2/3, the inverse of that would be raise both sides to the power of 3/2. So we're going to say to the power of 3/2 to the power of 3/2. So a power to another power, we multiply those guys. So on the left, that basically becomes t to the power of 1. Okay, so that's 1/3 to the power of 3/2, right? So 1/3 cubed is what, 27? Square root of 27? 9 times the square root of 3? So it looks like it's 1 over. And then we usually don't leave radicals in the denominator. We rationalize by multiplying by 1 like this. So then 27 square root of 3 over 27. That was a lot of like back and forth. But yeah, let me see. Critical numbers, all right? So our claim is that when t equals the square root of 3 over 27, that made the derivative equal to 0. And then also we need to go back and find what value of t makes a derivative undefined, right? So we do have that negative power. Is that inside of our, let me see, that's a 1, and 4 is what, 2? So that's like 1 point something. So I think that's what, less than 1? Okay, I think we're good because it's positive. Okay, so that's in our domain. Okay, so we had this term with this negative power. So that means what? When t is 0, that's going to make that undefined. So then our critical values, or our critical numbers, should be when t is the square root of 3 over 27, or when t is 0. It's a similar argument that we had from a question a moment ago, because we had a negative exponent. If t were 0, it'd create a 0 in the denominator, so it'd make the derivative undefined. So these are our critical numbers, these two here. Okay. And they're inside our domain. Notice that both of those numbers are inside of our domain. Find the absolute max and min. So with the absolute, so then once you have your critical values, then to determine the absolute max and min, you basically list out your critical values and the endpoints of your interval. You can only find absolute max and min when you're given like a closed interval. All right, so we got that -1 and that 6 along with our critical values. We're going to make a table. The absolute max is going to be the corresponding y, the largest corresponding y, and the absolute min is going to be the corresponding lowest y. So -1 and 6. Okay. So we're going to make a table. Let me see. So it's going to be what? T versus f of t? What was the function? Yeah, f of t. Okay. So from the, we said on the closed interval from -1 to 6. So we got our -1 here. We got our 0 here. We got our square root of 3 over 27. And then we got 6. Okay. We need to find the corresponding y. I do need a copy of the original. Okay. I'm just using that for reference. Okay. So let's go here. Okay. Let's go to our y equals, let me see, we got x minus x to the power of, now instead of doing cube root, I'm going to rewrite that as 1 to x to the power of 1/3. Okay. So then I want to calculate the corresponding y. So what I'm going to do is hit variables. So on the far right is a button that says clear. Just left of the clear button is a button that says VARS, which is short for variables. I'm going to go click to the right to go to y variables. Number 1 for function, and number 1 again to call on the function I just typed in. I want to evaluate this function when x is -1 to find the corresponding y. We got 0 there. Okay, so we got a 0 when x was 1. Let's see the value when x is 0. We got a 0 there. Let's see the corresponding y when x is the square root of 3 over 27. Got a negative point something. Okay. And then the corresponding y when x is 6. 4 point something. 18, 28, 79, 18, 28, 79, yada, yada, yada. Okay. So then we see that what? This is our max, and this is our minimum value. Okay. So this will be our absolute. Okay. I think I think those were all the parts. Okay. And so with that, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your evening. Take care. Peace. All right. Greetings, YouTube. All right. Beautiful mind here. So we have this question from Calculus. I'll just read it off, and we'll do the best we can. So this is question 12. It says, suppose that the volume V of a rolling snowball increases so that the rate of change of the volume with respect to time is proportional to the surface area of the snowball at time t. Show that the radius r increases at a constant rate. That is, the rate of change of the radius with respect to time is constant. Then it gives us the volume of the snowball is given by V equals 4/3 pi r cubed. So the rate of change of the volume with respect to time equals 4/3 pi. There's a blank times dr yada yada yada. Okay, let's start there. Let me see. So it says the volume of the snowball is given as 4/3 pi r cubed. Let's write that down. 4/3 pi r cubed. Okay. And then is write an expression for the rate of change of the volume with respect to time. So when it comes to like, this is another way, just writing derivatives like rates of change. Notice that in this expression there's no t, so we can't go directly from the volume to time. There has to be an intermediate step. Like if we take the derivative here, this is going to give us the rate of change of the volume with respect to the radius, all right? So I'm trying to think of how to. Okay. So again, there's no t here. So if we want to finish with the rate of change of the volume with respect to time, all right, we need an intermediate step. The derivative here is going to give us the rate of change of the volume with respect to the radius. But then when we take the derivative of the radius, we're going to say times the rate of change of the radius with respect to time. All right, that's just going to be something we're going to leave off to the side. Okay. So, but this guy here in the middle, this dv by dr, that comes from taking the derivative above, right? So I'll do this like this. So from here, when we take the derivative of the volume with respect to the radius, because again, there's no t there, this is going to be, the 3 comes down, right, and they're going to cancel. So we're going to have 4 pi r squared. And that's going to take the place of this guy. Okay. So then, basically what's happening, this is a crude explanation, but this is essentially what it is. So, you know, again, we can't go straight to the derivative of the volume with respect to time because there is no t here. So from here we can only get the rate of change of the volume with respect to the radius, and then we're going to say in another, like if we had a function for the radius times time, we would get the rate of change of the radius with respect to time. But since we don't have it, we're just going to leave it like this. So then what happens is basically this guy is going to cancel this, and we finish with our dv by dt. So what we're going to do is say the purple times the dr by dt, right? So then for the rate of change of the volume with respect to time, it's going to be this purple guy up here, 4 pi r squared times, and we're just going to leave this other one because we don't have we don't have that expression, so we're just going to leave it. And I think you had that part there. You can see, well, I don't think you have it typed, but you can see it here. 4 pi r squared, you can see it here. Right? So in that blank, I think would be this purple. I'll add another color. Whereas purple, orange, and black, that's what would go in that blank there. All right? So it says the volume of the snowball is given by this. So then the rate of change of the volume with respect to the time, when we take the derivative here, the 3 comes down. This 3 is going to cancel that. We're going to be left with r squared. It's going to be 4 pi r squared times dr by dt, right? Because we don't have an expression of the radius with time, we just leave it. You see it here, right? So the simple thing is really just this derivative goes in this blank, and you see the answer there. Okay. Now, they gave us additional information saying that since the change in the volume is proportional to the surface area, so I forgot what that meant. I had to look it up, but proportional just means that one function is going to be equal to the other function times some constant k, right? Like if we say that y is proportional to x, that means that we can write y is going to be equal to some k times x. So then in this case, it says the volume is proportional to the surface area. That means that we can write an expression where we say the volume equals some k times s, our surface area, right? So they give us our formula for surface area, which is 4 pi r squared. Okay. Now it says that the dv by dt is proportional to the surface area, right? So dv by dt equals k times the surface area, and that's what you have here. dv by dt equals k times the surface area. So that's a direct application of the definition of what we mean by two functions that are proportional. Again, it says dv by dt is proportional to the surface area. dv by dt is proportional to the surface area. Okay. So then the last part, we want to equate the two expressions dv by dt. Let me see. So we just want to simplify that. So now we just found in the first part that dv by dt was the 4 pi r squared dr by dt. Right here, 4 pi r squared dr by dt equals k times 4 pi r squared right here from the surface area. So then those 4 pi r squareds cancel each other out, and all we're left with is, so then here what you would have written was the 4 pi r squared. Right here would have been the surface area, 4 pi r squared. Okay. So then this 4 pi r squared would have canceled this one, and we would have only been left with the dr by dt equals k. So the rate of change of the radius with time equals a constant. All right. This again, that's a little bit back and forth, but that's about the best I can do. And it's a lot of it's piggybacking off of what they gave us, coupled with this notion of, which is not obvious, right here. It takes a little bit of a stretch to see that, like, okay, we can't go directly to the rate of change of the volume with respect to time because there's no t. The volume is expressed in terms of the radius. So only thing we can get from here is dv by dr, which is this guy, all right? And then since we don't know the relation between the radius and time, we just left it. But we needed an expression that had the rate of change of the radius with respect to time. Since we didn't know what it was, we just left it as is. So then essentially this guy cancels this, and we're left with our dv by dt. We're not actually going to do that algebra, but that's the setup. We have the purple, we leave the black. This was the expression, yada, yada, yada. So that part was a little bit, I have some other examples that kind of, I feel like is a better introduction to that, but But, you know, in this context, that's what it was, right? And then it was also an application of because the rate of change of the volume with respect to time was proportional to the surface area. So you got that one correct. That's so the dv by dt equals k times 4 pi r squared. Man, I really do feel like they're just like, it's, I don't feel like it's really, I don't know, I feel like they're giving you like challenging questions. I don't know. I've seen the same concepts, but it's not so like back and forth, you know, it's not so like all over the place. But anyhow. So then once we had our dv by dt equals k times the surface area, then we just simplified that. We took the answer that we got from the first part, compared it to that proportionality. The 4 pi r squared is canceled. The only thing that was left was the dr by dt equals k. All right, which is what we were trying to show in the first place. Okay, so hopefully that kind of helped some. Let me kind of write my notes here. So there should have been, we took the derivative, so the 3 came down. So it was 3r squared. Yeah. So in that first one, it would have been, right here, would have been 3r squared. I think that's it. And then the second one, I think it was 4 pi r squared. That 3r squared came because we took the derivative of r cubed, so then they gave us 3r squared. Down here, this came from the surface area that was given. All right. Okay. And you know how to reach me, because we can like try to do it live a little bit, but yeah, that was a little bit. I have some other examples I would use that I feel like it's a little bit more easier to grasp. But anyway, with that, we're going to end the session here. Now, from one beautiful mind to another, take care. Peace. All right, greetings, YouTube. Beautiful mind here. So, we had this question that comes from calculus. And at first glance, I was like, why is this giving me such a hard time? So then it dawned on me, I guess I'm used to teaching like business calculus. So a lot of that is like, introducing the derivative and things of that nature. We don't really use a lot of pre-cal. I totally forgot that like, other calculus courses are going to pull from pre-calculus. So for whatever reason, I wasn't thinking pre-calculus. Like I just don't automatically pull pre-calculus into calculus because most of the examples we do, we're not really using pre-calculus like that, but we could, obviously you can flow. So I had to put on my pre-calculus hat. I did some digging and some research, and so I'm going to start with this example that I found. Just digging research, using resources and pool. I found an example with an explanation, so I'm going to do my best to walk through it, and then we'll take some time to go through the one that we were assigned. So this question, this comes from section, I think it was 3.9. I lost track that quick. Yeah, I think it's 3.9, question 48 from the textbook, right? And so it says a Ferris wheel with a radius of 10 meters is rotating at a rate of 1 revolution every 2 minutes. How fast is a rider rising when his seat is 16 meters above ground? So most of this is actually pre-cal, right? And for whatever reason, it just wasn't on it. So it says it's doing a rotation, 1 revolution every two minutes, right? So that means what? The Ferris wheel is doing what? 2 pi radians every 2 minutes. All right, so it does 1 complete revolution. So when we're doing circles, right, we can talk about circles in two different formats, either in radians, which is like basically one complete revolution is 2 pi radians, or we can do degrees. It's going to be 360 degrees. For something like this, we're going to talk about it in terms of radians. So that's from pre-calculus as a whole thing. Okay, so it does one complete revolution, which is 2 pi radians every 2 minutes. So then if we simplify this down, let me see, did I get it? Okay. So what that's saying is that the rate of change of theta with respect to time, again, it does one complete revolution every 2 minutes, which simplifies down to pi radians every minute. All right, so when you simplify that down, we get this, okay? Let's see, it says the radius of the Ferris wheel is 10 meters, right? So that's this part from the center to the edge. We got it on there twice. One revolution every 2 minutes. How fast is a rider rising when his seat is 16 meters above the ground, right? So we're basically doing this as if the Ferris wheel is sitting on the ground. It's like we're not saying that the wheel is off the ground, just for the sake of simplicity. And so then we have our rider there, and we have a radius. We have our theta, which is like here. And then so we can use Pythagorean theorem to find the missing parts, right? So it says that the rider, we want to find out his angular velocity when his seat is 16 meters above the ground. So then his total height is going to be 16. He's already used 10 of the 16. So then that means that there's 6 meters left over for that h that we have there. So that h is going to be 6 meters, okay? And then I think from there, we can use Pythagorean theorem to solve for x, that other missing part. So then we'll say something like, so x squared plus h squared equals r squared in this case, in this context. So then x squared, h we just found was 6, so there's going to be a 6 squared, and the radius is 10 squared. So then x squared, 100 minus 36, 64, and the square root of 64 will be plus or minus, but in this context, we're just going to take a positive 8, okay? So then x is 8 meters. Let me highlight it. H is 6 meters, okay? Let me think. Now, if we took the cosine of theta, so SOHCAHTOA, right? SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If we took the cosine of theta would be what? X over 10. Let's just look at that real quick. So then cosine of theta would be x over 10, right? What am I missing? Okay, that's fine. Sine of theta, okay. So h, we want dh by dt. Let's back up. Okay, so let's do sine. So if we consider the sine of theta, that would be what? H over 10, right? And if we want the rate of change of his height with respect to time, okay, And then so this guy here implies that what h equals 10 sine theta, right? So if we want the rate of change of the height with time, so the derivative of sine is what, cosine? So then that would be 10 cosine theta d theta by dt, right? We took the derivative with respect. We took the derivative of theta with respect to time, so we tacked on that d theta by dt. But we also started with that, and we got it down to pi radians per minute. Okay. 10 cosine theta times pi radians per minute. Let me see. I'm almost there. And then for theta, and then for theta, we might need to do like an inverse sign. Let me see. What did they do up here? We have an expression for cosine of theta, derivative, right? Cosine of theta is basically x over 10, which is 8 over 10, right? So I think we got all the parts. So then that should be 10 times pi 8 over 10 meters per minute. Those units are meters per minute. We're just going to simplify it down. Let me add a page. Okay. So then that's 8 pi meters per minute. So I think for that example, that's how that goes. Let me check what they have. 8 pi meters per minute. Yeah. Okay. So let's do a quick recap on those components. And then, so now that we have a working example, pretty much our example is going to be essentially the same thing with different numbers, all right? So we have our Ferris wheel, we have a rider on it, we have a radius of 10, the Ferris wheel has a radius of 10 meters, all right? Okay. It says it's rotating at a rate of 1 revolution every 2 minutes. So that means the rate of change of theta with respect to time is going to be a complete revolution, which is 2 pi radians every 2 minutes. All right? That simplifies down to pi radians every minute. Okay? And then we're asked, how fast is the rider rising when his seat is 16 meters above ground? So we've already used the 10 here, so we needed to solve for this h. If we wanted a total of height of 16 meters, we say 16 minus 10, that's where h equals 6 came from. Okay. So then once we had h equals 6 meters, we can use Pythagorean theorem to find x, and we got 8 meters for x. So then once we had all the parts of that right triangle for that part, then we just we were like, okay, consider sine of theta, SOHCAHTOA, opposite over hypotenuse, so that's h over 10. And then so that means that we can express h as 10 sine of theta. But then we wanted the rate of change of his height. It might be, I feel like it should be plus, anyway. Yeah, we'll just let that be, right? So his h was 10 sine theta. So then the rate of change of his height with respect to time, we basically took the derivative of sine. We got cosine times d theta by dt, right? It's kind of like how we used to do it's kind of like the chain rule, right? Derivative of the outside function times the derivative of the inside function. We don't have an explicit expression for theta, so we just left it as d theta by dt. But that was a rate that we kind of explored initially. So then we basically plugged that in. We had 10. Cosine of theta came from the triangle, was 8 over 10. D theta by dt was pi radians per minute. And then once you kind of simplify everything down, we got down to 8 pi meters per minute. Okay, so that was that example. So then we want to take that notion and see, can we apply it to our example. Let me go like this. Let me see. Can I just get everything? Nice. This is exactly what I wanted. Okay, so let's apply what we just experienced in that example to ours. So now in this one, this is the one that we were given. A Ferris wheel with a radius of 15 meters, okay? So I'll do some changes in blue. So that means this is 15, this is also 15 here. Is rotating at a rate of 1 revolution every 2 minutes, okay? So then we'll say, the rate of change of theta with respect to time is 1 revolution. 1 revolution is going to be what, 2 pi radians? Every, what, 2 minutes. That's the same thing, right? Yeah, every 2 minutes. And then that simplifies down to pi radians every minute. Okay, so that's an expression for the rate of change of theta with respect to time. Exactly how fast in meters per minute is a rider rising when his seat is 24 meters above ground, right? Okay, so if we're going to do 24 meters above ground, 5 and 4 is what, 9? So that means that h has to be 9 meters, right? Because we want the total height to be 24, he's already used 15 from the Ferris wheel. So then 5 and 4 means there's 9 meters left over. So then we can use Pythagorean theorem. Let's go ahead and solve for x using Pythagorean theorem. So we have what, x squared plus h squared equals the radius squared, okay? We're solving for x, so we're just going to bring that down. The height, the h we got was 9, so we're going to say 9 squared. The radius is 15 squared, okay? I think that's 225 minus 81. I got a calculator. I'll just pull this one up. Oh, it's already there. Look at God. Okay, don't lose my page. I can still use my page. Let's go here. Okay. So we'll just do 15 squared minus 9 squared. Okay. And so then x squared is 144, which is 12. So then x squared equals 144. So then x equals 12. Okay. So we have h, we have x, and again that's meters. Okay. So now it says how fast in meters per minute is his height changing when the seat is 24 meters. So we need an expression that involves the height, and our theta, remember our theta is here, right there. Okay. Let's see. So h, so then what we would do is let's consider what the sine of theta, which is opposite over hypotenuse, is going to be h over 15. That's a whole pre-calculus thing. It's a whole, I mean, it goes deep. Like that within and of itself, that whole discussion on pre-calculus, this whole thing that takes a while. So anyway, all right, so sine is opposite over hypotenuse. So then that means, so from there we get that what, h equals 15 sine theta, okay? So then we want the rate of change of his height with respect to time. I'll work over here. So then it's dh by dt. It's going to be 15 derivative of sine, I think it's cosine theta d theta by dt, okay? Cosine of theta from the right triangle is going to be x over 15, which is 12 over 15. So let's plug in what we have. We got this 15. Cosine of theta is 12 over 15. d theta by dt is pi radians per minute. Okay, so then this is going to cancel this. It looks like if we did this proper, because basically what I did was mimic what I found, and kind of processed it a bit, but 12 pi meters per minute. Look, it's 12 pi meters per minute was our final result that we got there. Okay, so that's about the best we can do there. All right, let's just kind of show the whole thing for a hot second. All right. So with that, we're going to go ahead and end the session here. And from one beautiful mind to another, have a wonderful day. Take care. Peace. All right. Greetings, YouTube. Beautiful mind here. So we have this question that comes from, this is like Calculus or Early Transcendentals, 9th edition by, I think it's not Waters, it's like Watson. I forget the author. But this comes from section 3.9, question 25 from the back of the text. So again, what we did here was we found an example that was similar to our question. We found the solution, we walked through it, and then we're going to go back and from this example apply it to our question. So from this example, it says that water is leaking out of an inverted conical tank at a rate of 10,000 cubic centimeters per minute at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 6 meters and a diameter at the top is 4 meters. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which the water is being pumped into the tank. Okay. So, not obvious, but let's just walk through it. So we're going to let C be the rate at which the water is pumped into the tank. So I'll just kind of put it here. C is the rate at which the water is being pumped into the tank. Okay. So then the rate of change of the volume with respect to time is going to be what? The rate in minus the rate out, which is 10,000 cubic centimeters per minute. So the rate of change of the volume of the water is going to be the rate in minus the rate out, where the volume of the water is 1/3 pi r squared times h at any given t, at any given time t. Okay, so that's the main structure or setup there. So then we can use similar triangles, right? So we have like this smaller triangle inside this larger triangle. Okay, so then using the property of like similar triangles, we can say what? R over 2 equals h over 6. Okay, so then we can get an expression for r. So then this implies that r is what? H over 3 or 1/3 h. Okay, so that's an expression for the radius in terms of the height. So then let's take this and plug it into our volume expression. So then now we can express the volume. I think we can get the volume in terms of h solely, right? So that's going to be 1/3 pi. Now our r, we're going to substitute. Our r is now h over 3, or 1/3 h. And that's squared times h. Okay, so then if we keep going, okay, 9 times 3 is 27. So it looks like it's what? Pi over 27 times h cubed. Okay. So at this point, we have what? The volume in terms of h, pi over 27 h cubed. So then now we want to take the derivative. Again, notice that there is no t here, right? So we're going to take the derivative with respect to time, right? We kind of discussed this in the previous. I'm going to skip those intermediate steps and kind of just jump to the conclusion. But in both of these cases, we're taking the derivative with respect to time. So on the left, we're going to get dv by dt. On the right, the 3 comes down, what is that? Pi over 9, h squared, and then dh by dt. Right, we have to tack that on because we don't have an exclusive expression with h and t, so we just tack that on. Because we took the derivative of h with respect to t. Okay. So then the height. Now, the height of our water, it says when the height of the water is 2 meters, and all our calculations are in centimeters, so we do need to convert from meters to centimeters. So 2 meters is what, 200 centimeters? Okay. So we'll say when the height is 200 centimeters, again, just converting from 2, they gave us that the height is 2 meters, we converted from 2 meters to centimeters. So then, oh, and then the rate of change of the height, I think that was given to us as well. It says the water level is rising at a rate of 20 centimeters per minute, right? So then that's going to be our dH by dt, 20 centimeters per minute. That was given. So this was given. We got the height of the water. This was given. It was given in meters. We converted it to centimeters. Okay. So then there. dV by dt. Okay. dH by dt. Okay. Okay, so I think we have, it looks like we have 2 expressions for dV by dt, right? In one hand, we have the rate of change of the volume with respect to time is at c minus 10,000. Let me kind of compile some stuff. So dV by dt equals c minus 10,000. But we also have what dV by dt is this pi over 9. Yeah, pi over 9 h squared dH by dt. Pi over 9 h squared dH by dt. And then we had another piece of information that the dH by dt that was given was 20 centimeters. So dH by dt was 20 centimeters per minute. And we were also given that the height of the water was 2 meters, so that was 200 centimeters. Okay, I think those are all the parts. So then if we equate the first equation to the second one and substitute everything in, it looks like we get c minus 10,000 equals, we got that pi over 9, h is 200 centimeters squared, dH by dt is 20 centimeters per minute. Let me put my units so that I can make sure they work properly. So centimeters squared. dH by dt is 20 centimeters per minute. My m's, I don't even know what I'm writing today. Per minute. Okay. So we have one equation, one unknown. Only thing we don't know is c. So then from there is algebra. Not obvious. Again, I just did some digging and research. And this is this specific example. So then we're going to take this and see can we apply it to our example. So then the rate of the water in should be, we just have to calculate that. So we get this pi over 9, 200 centimeters squared. Okay. We got this 20 centimeters per minute plus 10,000 cubic centimeters per minute. So the units do match up. Okay, so let's do that calculation. This one. Okay. So let's do our pi over 9, 200 squared times 20, and then plus 10,000, I think. Plus 10, 1, 2, 3. Okay. 289, 252, it said round to the nearest integer. So 253, yeah. So this is approximately 289, 252, sorry, 253. Is it not working? Whatever. Here. Cubic centimeters every minute. Okay. So this was from the textbook, right? This was the example from the textbook. But the main takeaway, the main structure that we needed, the rate of change of our water was going to be the rate in minus the rate out. And then we also had we had an expression for the volume, right? Was 1/3 pi. Let's back up some more. Right here, the volume was 1/3 pi r squared at any given time. So then we got this. We use related triangles or similar triangles to get the volume in terms of h alone. So we said, we said r over 2 equals h over 6. R over 2 equals h over 6. So then we get r equals h over 3. So then we took that and plugged into our volume formula. We got our volume down to here. So then we took the derivative with respect to t, right? So right there and then here. And this derivative was like normal, kind of. Then, so now we had a second expression for the rate of change of the volume with respect to time. We were given that the height was 2 meters, so we had to convert it to centimeters. We were also given that the rate of change of the water was 20 centimeters per minute. So then putting all this together, we got all the way down to here. That was the example from the text. So, let me see. So then I need this image. Let me copy this. Guess that worked. And so let's pull up our specific example, which is this one. And we're going to have to make some changes to this image. Let's see. So the 2 and the 6 need to change. Water is leaking out of an inverted conical tank at a rate of 6,500 cubic centimeters per minute at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 6 meters, and so is it the exact same? No, right? Because the leaking rate is different. Because I think we had 10,000 before, right? Okay, so let's account for these changes. 6, blah, 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 20. I think that's the only change. Height of the water is 2 meters. Okay, I think that's the only change. So then, C is the rate in. C is going to be the rate water is pumped in, okay? So then the rate of change of the volume of the water with respect to time is going to be rate in minus, instead of 10,000, now the rate out is 6,500. Okay. And again, I'm just going to redo this. Let me see. The volume was 1/3 pi r squared h. And then we use similar triangles. So we said what? R over 2 equals h over 6. So then R equals h over 3. So then we took that and plugged it into our volume formula. 1/3 pi h over 3 squared times h. I think I'm okay. I'll just do it here. So then the volume equals h cubed. So pi over 27 h cubed. Okay. So then from here we want to take the rate, the derivative from both sides with respect to time. So then again, notice that there's no t there, so we got to do it like this. So then dv by dt equals, the derivative here becomes, what is that? The 3 comes down, pi over 9 h squared, and then we got to tack on this dh by dt. Okay. Let's see what else we were given. I think the height of the water is 2 meters, so our h is still 200 centimeters. Right, we had to convert from 2 meters to 200 centimeters just like before. And then our dH by dt, it says the water is changing at a rate of 20 centimeters per minute. So our dH by dt is 20 centimeters every minute. Okay. So then I think we equate these two expressions. All right, I'll go ahead and put the second one next to it. All right, earlier we said that dV by dt was C minus the 6,500. All right, both of those equal dV by dt. Okay, so long story short, we can isolate C. C is going to be equal to pi over 9. Our H is 200 centimeters squared. dH by dt is 20 centimeters per minute. Okay, and then plus 6,500 cubic centimeters per minute. Notice that the units are going to match, and then from there, it's a calculation. It's a calculator problem at that point. I'm just going to recall what I had before. 200 squared. So instead of plus 10,000, it's plus 6,500. I think everything else is the same. So then nearest integer, 285,753. Centimeters every minute. Okay. All right. So again, that one I just did some research. I was able to find this and kind of walk through it and kind of walk through an explanation. Okay. Not obvious, but none of these are really intended to be obvious. It's like it's an experience, and it's like, basically through trial and error you come across it. Some of the stuff you can process, but many of it you just got to have an experience to figure it out and dig and research and stuff like that. Okay. Just trying to get the whole thing. All right, and so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace. All right, so yeah, um, so most of that I was kind of doing off the cuff. I think the last two questions I had to dig and research. Um, you know, we did the best we could. So with that, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.